Good morning, good afternoon, and good evening, everyone, wherever you might be. And today we're going to be doing a little bit of exercises on cylinders and quadric surfaces. So yeah, let's just hop right into it. So for our first one, we want to determine, um, okay, it's actually a set of numbers here. So our first problem here is we want to determine what's the name of this curve. So what does the equation y equals x squared represent in r squared? So this is in 2D. And so in 2D, this would basically look like this. And so this is a parabola. That's it. Next, um, what does it represent as a surface? So here we're now talking about a quadric surface. So what does it represent as a surface in R cube, right? And in R cube, we have three variables. We have x, y, and z. And here we say y is x squared, z is nothing. So how does that look like? Well, if we draw our curve here, so this is x, y, and z. Y equals x squared is in the xy plane, right? And so this would look basically like this. A parabola concave up, right? And since z is 0, it's gonna keep, it's actually infinite. It's gonna keep going up and down from the z-axis. So maybe this shape would look like this. Kind of like that. So this is a parabola, but in 3D, and one of the variables is 0, so we call this a parabolic cylinder. So that's what it represents. Okay. Oh, that's it. Okay. Next thing we want to do, number 2, here we're given an equation and we want to describe what kind of surface is it. So here we're given this y squared plus 2z squared equals 2. So here we're describing it in 3D. Here we can already tell that x is 0 by default because there's no x. We have y squared and 2z squared is 2. And so we know that if we were to draw this in 3D, the surface would be somewhere in this x-axis because x is 0. So it's going to be revolving around the x-axis. Now here we see a positive sign and we see that both y and z are second degree. So what does that tell us? Well, this tells us this is some sort of ellipse. So this is some sort of ellipse. The trace in YZ plane, um, Yeah. So it'll probably be like some sort of ellipse. And then since x is 0, it's just gonna go somewhat infinitely. Okay, my drawing's bad. It looks like a log. So this is what we call an ellipsoid or an elliptic cylinder. An elliptic cylinder. We say cylinder because this goes infinitely in the x-axis. So it's an elliptic cylinder. Now we want to, okay, it does sketch the surface, but I already did it. Mm, okay, so what are we gonna do? We want to write an equation for the cross section at x equals -2 using y and z. So if x was -2, how would that look like? Well, here we're just drawing an ellipse at exactly x is at exactly x equals -2. So we're drawing the ellipse somewhere in this area here where x is -2. Right. I think that's what we're supposed to do. Um, okay. Oops. Let me just do that real quick. I'm gonna write the equations. It's pretty much the same thing. Um, we're just writing the ellipse at that exact position. So I'm just gonna write it. Yeah, so again, it's an elliptic cylinder. Now we write an equation for the cross section at x equals -2. It's pretty much the same thing. Yeah, it should be the same thing because it doesn't change no matter how we're altering it, right? Let me hit submit and see what happens. But I feel like it doesn't change anything. Oh, yeah. And then when x is 0, it's the same thing. When x is 2, it's still the same thing. Because z is not being altered at anything. Yeah. Okay. That was simple. Okay. I'm not gonna share that anymore because I literally typed in this equation, this one, when x is 0, when x is 2, when x is -2, because at the end of the day, it's gonna be that same ellipse. Right? Okay, let's move on. So now we have another similar question where we also describe the surface. And so we have our equation z equals 3 minus y squared. So what is this? Well, here we can assume again that x is 0. And so if x is 0, Well, this revolves around the x-axis, right? So if I were to draw, okay, so far I can draw these stuff because they're pretty easy to visualize. But when I get to the more complicated quadric surfaces, then I probably can't draw them anymore. But yeah, here, x could be anything. 3 or 0. 3 minus y squared is the curve, or we can trace that along the yz plane. So this is just going to be a downward parabola that goes up to 3. So maybe, I don't know, something like this, where this is exactly 3. And since x is nowhere to be found, then yeah, this is just infinitely something like that. Oh, give me an ugly looking graph. Yeah, so something like that maybe. So this is a parabolic cylinder. It's a cylinder because x could be anything. You know what? Instead of me saying x is 0, because that's the easiest to trace when x is 0, we can say z is some value k, where k is any real number. And then we can do the same thing for here. Here we say x is some value k, where k could be any real number. Then same idea here. Okay, so that's a parabolic cylinder. And then again, we want to sketch the surface when z is 0, y is 0, and x is 0. So here this is actually going to be different. Because previously, which I did not show anymore, here we were asked, what if x was 0? What if x was 2? What if x was negative 2? Then it'd be the same thing. So here I'm actually going to write this one out. So here we're being asked to write an equation for cross-section at z is 0 using x and y. So when z is 0, well, we just have 0 equals 3 minus y squared, right? Because that's when z is 0. We don't have x. X could be anything. So that's it. Pretty much. That's it. We're gonna type that in. 3 minus y squared is 0. Submit and see. Whoa, what's the lag? Okay. Next, we do the same thing. So I'm just gonna copy paste. Okay, I'm gonna put it up. But here we want when y is 0. When y is 0, we're now using x and z. But here really we just make y 0. That's it. So z is 3 minus 0. So z is 3. Pretty much. That's it. Okay. And now we do the same thing when x is 0. So here we're just really plugging in the stuff. We're just plugging in when a variable is 0. So here when y is, I'm kidding, when x is 0, I believe. When x is 0, it's just the same as the first one we did. Because no matter where our x is, we'll still have the same curve. So it's just this. Done. Nice. Okay. Next, we actually have a nice visual here, but I actually can't see the visual. Okay. Another describe the surface question. Okay, so to describe this, here's our curve. So what is this? Well, if we were to draw our space, this is in terms of the YZ plane. So that we can trace this using YZ plane. This is just the sinusoidal function. So it just goes like here, up, down. Maybe like that. And here, x is again some value, some real number. And so this just keeps going here. And then we just keep. Okay, I'm gonna try my best and see how well we do these drawings. Okay. Just trust that this is exactly how it looks like. So it's like wavy-ish. And this is again another cylinder. But what kind? It's a sinusoidal cylinder. Because of the sign, that's where they got the name. It's a cylinder because x goes infinitely. That's it. Now again, we want to write an equation. So let's quickly do that. So here we just replace everything with zeros. So write an equation for cross section at x is 1, I mean -1, using y and z. Basically, we just need to plug in where x is negative, then we're good. Oh, look at that. No x is -1. So we just have the same curve. Done. And we do the same thing again based on what we're being asked. I'm just going to copy paste. Okay. So here the next thing we're being asked is to write an equation for the cross section when x is 0. And then lastly, when x is 1. Which honestly, they're all the same thing. Because wherever x is, we have, that's the answer for that one. That's the answer for this one. So it's really that easy. Maybe I shouldn't have written it anymore. I'm gonna type it in. So z is equal to sine y. That's it. Done. Quick and easy. Okay, next. So in the previous video, I had a hard time doing this, and I learned of a strategy from my professors, which I'm going to incorporate in these exercises. So here we're being asked to find and identify the traces given the equation of a quadric surface. So let's quickly do that. X squared plus y squared minus z squared is equal to 49. Given the plane. And our plane here is x equals k. So here we're actually trying to plug in k to x. That's all we have to do. And then we're going to use this thing called the thumb method, where we remove everything of x and we swap it to the other side, so that because k is some constant number, and we're left with some equation. So when we do that, we have k squared plus y squared z squared. So here note that k squared is some number, right? And then we swap it to the other side. Now this is some constant. This is a number, and this is the one we're given. So we can even imagine this as like y squared minus z squared equals 1. We can do that. But we have to focus on this one. This is what will help us identify the trace. So here we notice that both variables are squared. They have second degree. And here we also notice that there's a subtraction. And so if that's the case, there's a subtraction and they're both second degree, that means they're a hyperbola. They're a hyperbola. That's what it means. So here we say that this is a hyperbola. That's how we identify that trace. And this is also our equation. We could do the first one, doesn't matter. So if I put that in, knowing that this is a hyperbola, so y squared minus z squared equals 49 minus k squared. Yeah, it's a hyperbola. Let me just double check just to be sure. Yeah, yeah, if it's subtraction, it's a hyperbola. Yeah. Let me hit submit and see what happens. Nice. Okay, next. Now we have another plane here, which is y is equal to k. Again, we find and identify the trace. We're using the same quadric surface equation. So if y is k, then we just plug in y is k. So x squared plus k squared minus z squared equals 49. And again, we uh, subtract k squared to both sides to put to the other side. And so this is our trace. Now, what do we notice? We just log these terms. Same idea. We have two variables. They're squared, and there's a subtraction. So again, it's a hyperbola. This trace is a hyperbola. So let me just type that in. Someone could even do this mentally. I'm just going through it step by step just to be sure. So yeah. And now this is the same hyperbola, but in the xz plane. The other one was in the yz plane. So again, it's a hyperbola. And lastly, we can also do this last one before we try something else. So z is k, we do it again. If z is k, now we're looking at xy plane. So again, we plug in. So we have x squared plus y squared minus k squared equals 49. Then we just simplify this thing, and there's our trace. Now what is this? Well, if we look at the two variables here, now it's not a hyperbola because of the addition. Oh, look, it's a circle. Or it could be an ellipse. Which is basically an elongated circle. But yeah, that's that. Mm. Oh, okay, now this is interesting. It gave me the choice between a circle and an ellipse. So which one is it? I'm gonna say, hmm, I'm actually gonna check because I'm also questioning that. Okay, apparently it's a hyperboloid of one sheet. Yeah, if z is k, is it a circle or an ellipse? Oh, so it's a circle. Why? Because the numerical coefficients are equal and they're both one. Now, the moment if something like a 5 pops in one of them, and then this one's still 1, that's going to make it an ellipse. Or let's say this is divided by 4 divided by 3. That's going to make it an ellipse. Because their numerical coefficients are not equal. So this is a circle. Yeah, if z is k, this is a circle. Let's just type in what we found. Okay, x squared plus y squared equals 49 plus k squared. And that's a circle. And now, can we describe what kind of shape this is? Well, we have two hyperbolas. So it's a hyperbolic, and then we have a circle. So what is that? Well, it's a hyperbolic something. Definitely it's a hyperbola. Is it a hyperbolic paraboloid? Definitely not, because there's no parabola anywhere. Now, is it one sheet or two sheets? Two sheets meaning they don't intersect. But here you can see this is a circle. So they do intersect. So it is a hyperboloid of one sheet. That's what it is. And I cannot draw this. I tried in the last video and I suffered. So it's really more about just identifying the characteristics of the shape and then determining what shape it is from there. But drawing wise, it's really hard for me. So describe the surface from one of the graphs. We're actually given a table here, which is funny. I can copy this table, I guess. Oh, I did not mean to do that. I can log this table and I can see, oh, it's a hyperboloid of one sheet. Because the horizontal trace, the xy plane, is an ellipse or a circle. So here. And the vertical traces, so the yz and the xz are both hyperbolas. Now, another way to check, we have two sheets here. Vertical traces are hyperbolas, and there are two minus signs, which indicates two sheets. And here in the beginning of the equation, we only have one minus sign. So immediately, it's not a hyperbola of two sheets, or hyperboloid of two sheets. So it's definitely a hyperboloid of one sheet, right? I can refer to the table, but I don't know. I like my professor's strategy better. So I'm gonna stick to that. I can do a review of the table, like just to also double check. Hyperboloid. And I'm gonna mess up my spelling of one sheet. Yeah. What else? Okay. We have some questions here, which that was interesting. If we change the equation in part A, how is the graph affected? So some altering stuff happening here. So if we change, so let's say we change this thing. X squared minus y squared plus z squared equals 49. What's gonna happen? How is graph affected? I'm intentionally not putting the and the other English stuff because I don't really care. This is not an English class. But anyway, so we have that. What was the original? We put the negative in the z. How did that affect it? Well, whenever we put the negative, so see here, the axis of symmetry corresponds to the variable whose coefficient is negative. So z here has a negative coefficient. And so that's where it's symmetric. That's the axis of symmetry. It's here in z, which I mentioned in my last video. But now here, the z is positive. So that's not the axis of symmetry, but instead it's in the y part. So what's going to happen is the axis of symmetry will turn to y. So if I log the options here, the right answer would be, or I think, I'm still going to check. The graph the graph's rotation will change from z-axis to the y-axis. So I'm not going to draw a graph for a bit, but just a rough idea of how this might look like. Z, X, Y. So initially it was something like this, the hyperboloid in one sheet, where it's revolving around the z-axis, but that's going to change. Now it's going to be in the y. Oh, maybe like that. Now it looks like a laboratory apparatus. Let me cook. Let me cook. Okay, but you get the idea. So it's now sideways. I'm not gonna draw. Yeah. Ooh, now this is another interesting one. What if we change to this thing? X squared plus y squared plus 2y minus z squared equals 48. Now what would happen? Um, so here the original was x squared plus y squared minus z squared is 49. And then we added this 2y, and then this became 48. So initially, it's revolving around the z-axis. It's still revolving around the z-axis because of this negative here. So that doesn't change. But it's apparently something about shifting, right? So it's something about this thing. And if I allow my little cheat sheet here, given that we have this like whole equation here, this basically means you can translate some stuff, right? I think it was this one. You can translate. Maybe, I'm not sure. Let me go through my professor's other notes. Yeah, it's mostly just shifting and maybe translating. Um, so it's this idea. So it's probably shifting. So I'm gonna say the graph is probably shifted 1 unit in the positive y direction. I might be wrong though. So we'll have to check that. Yeah, I'm gonna check it real quick. Now, how would that differ? Yeah, we can complete the square. Oh, but then it shifted 1 unit. because I did a completing the square. So actually the way to see this is completing the square. So that's what we want to do. So this piece here, y squared plus 2y, we can translate that to y plus 1 squared, right? And then this became 48. Initially it was 49. So there's that extra plus 1, and then we subtracted it, so this became 48. So this is completing the square. And now what happened here? Well, we get x squared plus the completed square 48, right? So yeah, that's what happened. And here, see this? Y is shifted by 1 unit in the positive direction. I have to be specific. In the positive direction, positive y direction. I have to be specific. So that's what happened. Yeah, I was right, luckily. Okay, let's submit all of that and see what happens. Nope. Oh, okay, apparently that's wrong. Don't know why. Graph is shifted 1 unit in the positive y direction. Well, that's interesting. Oh, it's negative. Oh, yeah, because it's plus. Yeah, this had a formula which was like, this is basically the same as y minus -1. So it shifted negative. Careless. Okay, so that's the negative. Yeah, definitely not rotating. Okay, nice. Okay, now some matching here. So let's quickly do that. Match the equation. So I guess a way we can do this is identify what are the traces and then match it from there with some graph here. So this is interesting. Here we're given what's even cooler is if we could draw it on our own. But I can't do that. I can't do that. So yeah, if you watch my previous video on trying to draw quadric surfaces, that's just me going in circles and my brain is okay, I'm not gonna say anything. Okay, so we have to match the equation with its graph. So I think a good way to do this is to identify the traces. And that's what we also did in the previous video. And that is if we make x, y, and z into some k value. And that means they're constant, right? So let's quickly do that. So if we say x is some value k, um, so we say k squared plus 49y squared plus 64z squared is equal to 1. We flip that k squared to the other side, so we get 49y squared plus 64z squared equals 1 minus k squared. And this is again just some real number that we don't know. Now we want to focus on what this is. So I'm going to underline it. This is, we have a positive, and we have 2 here, and we have different numerical coefficients. So this is an ellipse in the YZ plane, right? And we do the same thing. Let's say if we make y some real number, then we just plug it in. So x squared plus, what's this, 49k squared? Yeah, I can do that. 49k squared is again just some number. Plus 64z squared is 1. Then we can simplify this, or we put this in the other side. So now we have some number, and this thing. So we want to focus on this thing. What is this? Again, we have 2 variables. They're both second degree. There's a plus, and then they have different numerical coefficients. So they're an ellipse. And lastly, if we do z, and z is, okay, let's just plug in the stuff. 49y squared plus 64k squared equals 1. Then again, we keep on switching, and oh boy, we have another ellipse, right? An easier trick would be cover x. What do we get? Ellipse. Cover y, what do we get? Ellipse. Cover z, what do we get? Ellipse. So these are all ellipse, the traces. I did not say traces. Identify traces. So now we know they're all ellipse. So I'm going to look at some of the graphs here and check which one looks exactly what I'm trying to find. So this is just a process of elimination. I think this one matches it perfectly, but I'm not super sure. Oh, where did I copy paste it? Oh, there you are. It could be either this guy, right? Why do I say it's this guy? Well, again, from all the planes, their traces are ellipse. This looks like an ellipse from the XY plane. This looks like an ellipse from the XZ plane. And this looks like an ellipse from the YZ plane. Or it could be this one. Yeah. So again, from the XY plane, this definitely looks like some ellipse. From the XZ plane, this looks like an ellipse. And from the YZ plane, this looks like an ellipse. I'm just going to keep getting smaller and smaller and smaller. So which one is it? Well, that's where our purple lines come in. So from YZ, we have 49 and 64. How does that look like? From the YZ plane, okay, clearly this one seems off. Kind of. Kind of seems off because it looks like a circle. This one though looks really realistic for an x for a YZ plane if we have 49 and 64 as numerical coefficients. Then we have x squared plus 64 z squared. So here I'm just looking at their numerical coefficients at this point. So for xz, it looks good, right? Because z is going a bit up and x is just there. It's not elongated because that's what numerical coefficients are doing. We have a circle. Let's say we have x squared plus y squared. This is probably some circle. And then if we say 2, or let's say 100, 100x squared plus y squared, then it's going to be stretched horizontally. So it's kind of like stretched. And then if we say like x squared plus 100y squared, then this is stretched like that. So that's what I'm trying to say. Here, if we look at our x squared plus 64, we're kind of stretching the z here. We're kind of stretching the z. If we look here, it looks like we're stretching the x. Yeah. Yeah, see this cross section? It looks like we're stretching the x, but that's not the case here because we're stretching the z. And then for our last part is this xy plane. So xy plane kind of looks like a perfect circle here, funny enough. Here though, looks a bit stretched to the x part. So I wouldn't say my best guess is it's probably this one. Yeah. So I would say it's that. I'm gonna watch a video just to see. Yeah, but when we're sketching, we want to identify. So the way the video did is he did brute force. Like he made sure to actually look at those traces. Um, I could try doing that, but then again, it's really just best guesses for now. But to be really sure, I'm gonna graph it in my Desmos just to see what it actually is supposed to look like. So let me just do that real quick. So, okay, what was the, oh, I had 3D. Okay, I'm gonna quickly graph the thing. I want to see how it looks like. It's 49 y squared. I mean, if you guys have some tips on how to like graph this thing, then I probably need it. Is equal to 1. Oh, okay. So apparently it is an elongated ellipsoid. It's an ellipsoid that's like this thing here. It's referring to this one, not this one. I mean, I guess it's what, like point plotting or y is less than z here. The number of the numerical coefficient of y is less than the one in z. I guess I can check here maybe. I'm gonna be honest, I cannot tell. Oh, another way you could check is where is it revolving at? So here it kind of looks like they're both at the Z, which I guess makes sense. But then when you're given like this thing, huh? Apparently this is the answer though, based on what my graph is saying. I can't quite reason it why. 49 and 64. How would that look like? Let's say I'm gonna do it in 2D. Y and Z. 49 and 64 would be like what? And then we have some value here that we don't know. So it's longer on the Z side, but shorter on the Y side. It's like maybe like that. Can't tell really. I'm actually gonna try and look up 8 decimals just to see how that looks like. But let's do it. Yeah, I'm also curious. Squared. Oh, what happened? Plus, is it 60? 64 Z squared equals, let's say, something like 5 or 100, or I don't know. Oh, yeah, it is like a stretched ellipsoid here. Wonder why. I guess it's point plotting, intuition, no idea. Yeah, it's kind of getting elongated. Yeah. Hmm. So it makes sense to say it's this piece here. So it's kind of getting elongated like that. Yeah, I would say that's really difficult for me to. I'm not good at geometry. But yeah, this is the graph apparently. Okay, so let me just plot that in and see how we go from there. Um, yeah, apparently it's this one. Submit and see what happens. Okay, we got it. Yeah, that one's one of those things where I'm just like, no way. Okay, let's do more of these matching stuff. Match with graph. And here we're given another equation here. It's just, um, let's do it quickly this time. So we have x squared minus y squared plus z squared equals 8. I'm actually going to try tracing it maybe for a bit. So here we see if we block the x, then we get negative y squared plus z squared. What is that? That's z squared minus y squared, so that's a hyperbola, right? So we can say it's a hyperbola in YZ plane. That's really how we're going to be looking at it. So in the YZ plane, we have a hyperbola, X, Y, Z. Let's do it in red. So YZ plane hyperbola would look like going up and down, right? Also because it's the Y direction. I don't know how that's gonna look like, but basically it's gonna be, I don't know, something like this. and then maybe something like this. Not super sure yet. Okay, let's check another one. So let's say we block this y. It's positive and they're both second degree, so it's an ellipse. In xz plane, right? So let's do it in blue. XZ plane is this plane here. An ellipse would be, no, actually it's not even an ellipse, it's a circle because their numerical coefficients are equal. Circle with radius 2 square root of 2, square root of 8, so 2 square root of 2. I'm gonna say maybe here, some circle, right? In the XZ plane. And lastly, our horizontal part. So we take out that z, we get x squared minus y squared is 8. So here it's another hyperbola. In xy plane. So we have a hyperboloid and we have a circle. Let's do it in green maybe. Maybe somewhere here maybe. Yeah, pretty much. So how in the world does this look like? Well, if you look at our table, which I'm actually gonna do real quick, it's a hyperboloid, but which one? It's one of these. Horizontal, so vertical traces are parabolas, are hyperbolas. That's what we're sure, right? YZ is vertical, XZ is vertical. Oh, so it's YZ and XY. So it's not one of the hyperboloid in one sheet and two sheet because not all vertical traces are parabolas, are hyperbolas, I mean. Oh my goodness. X. It's not two sheets, no? Because there's no negative on, there's no two minus signs. Um, let me think. Let me think. Here at, what is this? So YZ plane, XY plane. Hmm. Oh, we want to rotate it to the other side because we're revolving around the Y. Here it assumes we're revolving around Z. So if we're revolving around Y, we have two horizontal traces, or two vertical traces that are hyperbolas, right? Okay, I'm gonna do this for my sake as well. If I rotate, probably in an exam, I'm just gonna. Oh, I can't rotate it. Oh shoot, that's not good. Okay, but just imagine this is rotated, so the green thing is above, and so this is vertical. Okay, I'm actually tilting my head sideways. This is vertical, the XY plane, and then another vertical is the the YZ plane. So they're both vertical. And then the horizontal is XZ plane. So it fulfills that one in the table. So this is a hyperboloid of one sheet. Yeah, but that's just sidewards. So it's I bet the graph is gonna look something. I don't even want to do it. maybe how in the world would that look like? Like that, maybe? And then I kind of okay, let me cook. Let me cook. Let's try drawing again. Uh and it goes out like that maybe. And goes here. There. There. And then it goes like that. Yeah, 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 yeah. And then again it goes up like this. It goes down like this. It goes down like this. There. And so imagine it's something like that. Now I'm gonna look at the picture that looks better. Oh, there's one that looks super, super better. It's this picture here. So I'm guessing it's this one. But again, I'm gonna, just to be sure, I'm gonna check using Desmos. There we go. Love that. Much better. Okay. There. That's it. Let me look at Desmos just to be sure. Um, X squared minus Y squared. Whoa. Okay. Plus Z squared equals 8. Okay, it doesn't show me anything. Um, X squared minus Y squared plus Z squared is 8. Why is it not showing me anything? 10, 1, 2, 3, 4. How do I? Oh, there we go. Okay, okay, okay. So it's I don't know, it kind of looks like that ish. Yeah, that's my best bet. That's that one. Okay, I'm gonna see if I get it. Sketching this is really hard. Like getting the exact one. Okay, got it. Okay, we have two more. I might just go through each of these. Uh, okay, let's go through each of these actually. So for 8, I also need to, oh, why did I make it purple? I also need to practice matching these stuff with a graph. So not necessarily sketching it. Okay, so we have negative x squared plus y squared minus z squared equals 9. So we take out x. So in the yz plane, it's a what? It's a hyperbola. Done. We take out y. It's two negatives. So actually, automatically, this is a hyperboloid in two sheets. Yeah. So this is immediately two negatives. So hyperboloid in two sheets. Yeah. And we can check the last one, which is again a hyperbola. If we take out the z, it's a hyperbola in the xy plane. And so how would that look like? There's only two sheets here, hyperboloid and two sheets. So I'm just gonna copy that and paste it here. And I can at least show where the hyperbola is in each plane, where the traces are. At least that I can show. So here it's in two sheets, right? It says we have a hyperbola in the YZ plane. Where in the world is that? YZ plane is this plane. And so the hyperbola there, well, it's actually sort of, ideally it's something like this, right? And so I guess it's this one to be more realistic. And it just keeps going on and on and on. And then the two negative signs means there's no intersection here at this plane, right? Another reason why it's revolving around the y, because y is positive, right? If we look at the table here, I don't know if you guys can see, but here the x and the y, some a and some b, the x and the y are negative, but the z is the one that's positive. That's why it's revolving around the z. But here it should be revolving around the y, because that's the positive one. So it's revolving around this thing. What else? So it's in two sheets, and again, there's a hyperbola in the xy plane. So the xy plane is this thing. Now, where is it? Well, this one I think is the easier one. There. So in 2D, it would probably look something like this. Yeah. So that's that. We're gonna try, see if it works. If it doesn't, that's okay. Okay, we got it. And last, match equation with graph. So we do x squared plus 7z squared equals 1. And we have, okay, so here this is a cylinder, because here y is any number. So it's a cylinder. And here we notice that, oh, x squared plus z squared, this gives us an ellipse because it's positive and they have different numerical coefficients. So it's an elliptical paraboloid. No, elliptical cylinder. Yeah, that's revolving around the y-axis. So what description fits that the best? An elliptical cylinder that's revolving around the y-axis. Um, Probably this one, I'm gonna say. Here I'm just looking at what's the best one. I think this one maybe, right? Because it's an ellipse. Um, in terms of the xz plane, and that ellipse just keeps growing and growing and growing. Um, and it's revolving around the y-axis. So it's definitely an elliptical cylinder, but just to be sure, I'm gonna check it. Okay, I'm actually zooming in here. Oh, it's literally a cylinder that's flat. Um, oh no, there's a parabola, so it's not this. Yeah, my bad. Oh, it's probably this. This is the best one I can find. That's the closest. But the Desmos one looks better. Yeah, I forgot because in the XY plane there's a parabola. So it's not, I don't think it's this one. Actually, I think it's this one. Here's a cylinder, but apparently this is a circle, but this is the best one we can find. Hmm, the other one's revolving around the x-axis. I can't tell, so I would say, I would have to say it's that. Yeah, it's revolving around the y-axis. Yep, it's just not drawn to scale. Let's see if we got it. Nice. Okay, number 10. Here's where it gets interesting. For number 10, we want to consider equation below. So I'm assuming it's an equation of a quadric surface. So we have 10x squared. We subtract that to y, and we add 2z squared. And we equate that to 0. And we reduce the equation to one of the standard forms. Oh, so we want to base it on the table and reduce it to a standard form here. See, that's hard. First thing I want to do before reducing it is I first want to identify what it is, and then I'll just look at the table and reduce it from there. So what kind of curve is this, or surface is this? So I'm going to do it in a shortcut. So I'm going to say, take out the x. We have this thing. Oh. So here we can say negative y, or actually we can say y is 2z squared. This is a parabola. So I'm going to say um, parabola in YZ plane, right? Now we can take out the y. Oh, this is an ellipse in XZ plane. And I do it again. Take out the z. Oh, this is another parabola. Y equals 10x squared. In the XY plane. So what is this? Well, it's definitely a parabola. It's a paraboloid of some sort. And we have this one information about ellipse. So if I were to look at my table, um, what is it? Well, it's an elliptic paraboloid. Pretty much. That's what it is. So this is an elliptic paraboloid, right? Why? Because the horizontal traces are ellipses. What's the horizontal trace? Here I can imagine it's revolving around the y-axis because the y-axis is negative. And so if I were to draw this from the y perspective, let's draw it in z first and see how it looks like in y. So z, x, y. We flip the y around, so now we get, oh god. If we flip that y around, now this is y, z, x, right? So it's a parabola in the yz plane. What does that look like? YZ plane is this plane here. So it's a parabola there. So this is vertical, right? Vertical. So I actually need to also identify, is it a vertical trace or a horizontal trace? The ellipse is in the XZ plane, so this is horizontal. And then the XY plane, which is a vertical in this case, is a parabola. So in this case, yeah, it's an elliptic paraboloid. Now I want to reduce it to standard form. So how do I do that? Well, standard form for an elliptic paraboloid based on the table is this form. But we assume here that it's rotating in the z-axis. So we might actually want to change it up a bit. We want to put the y on the other side because that's the one we're rotating. So we say y is 10x squared plus 2z squared. And then we can divide everything by 10. Or by 2, actually. Let's divide everything by 2. So this will give us y over 2, 5x squared plus z squared. Yeah. And then now this is in standard form. I could have divided it by 10. That's fine. But this way seems okay to me, I guess. So I would say this is my standard form. I'm actually going to type it out and see what I get. Okay, y over 2, we equate that to 5x squared. And then we add z squared. And let's classify the surface, which you already did. It's an elliptic paraboloid. And again, we're sketching the surface. Okay, let's quickly submit and see if we got the standard form correctly. And if we identify the curve correctly. Okay, we didn't get the standard form correctly. Modify your answer. But we got the elliptic one, right? It's just this part. Okay, let's see. Maybe I have to put z on the other side. Maybe. Yeah, here isolated y. Maybe I have to. Maybe it's the Z I need to isolate, but I don't think so. I think I got it. So yeah, I honestly I don't know why I would I don't know why my homework's telling me to do it that way. It doesn't make sense to be honest. I could take out the y equals 10x squared. I could do that. Plus 2z squared. I don't know. Okay. So instead of oh that's weird. Because I could just make it like this. Um yeah, that's super weird. Okay, let's do something else first while we're doing that. That one's really weird. Here we're being asked to write an equation for the cross section at z equals 0 using x and y. So here we just make z equals 0 in this thing here. And so that would be 10x squared minus y equals 0. That's it. It would be y equals 10x squared. So if we want to be really specific, there. Just make the 0, we have 10x squared minus y equals 0. Add y to both sides, we get y equals 10x squared. So it's a parabola. Okay, let's do the same thing, but this time, let's do it for y, I think. Y is negative 2 using x and z. Negative 2 using x and z. So if my y is negative 2, I just, again, plug it in this original. So 10x squared minus negative 2 plus 2z squared equals 0. So this is plus 2. So again, it gives me this thing, right? What else? I could put this to the other side. Negative 2. And so this equation doesn't make sense because it's negative on this side. So this is basically impossible. Is it though? Can we draw a graph of this? Yeah, if we do draw a graph of this, this is the equation of that cross section, which means there's no solutions for any of them. For any x and z to give some negative 2 value. Yeah. So 10x squared plus 2z squared equals negative 2. How about if we do y equals 2? Now we have something, right? So if my y is exactly 2, then I get this. Oh, crap. Instead of -2, I get -2, so I got +2 at the end. So this might be possible. So x squared plus 2z squared equals 2, right? We do it again. This time, we make x equal to 0. And here we're using y and z. So if we look at our previous equation, we can just cancel out this x. We get negative y plus 2z squared equals 0, so we get y equals 2z squared. So this is really just some simple algebra. Y equals 2z squared. Done. Okay, let me try again, especially with that standard form, because that one's bugging me out. Oh, we got it, but okay. Y equals -2. Okay, I did something with the cross section. I just plug it in, right? Did I mess up something? Minus, okay, I have this. I equated it to 0. Oh wait, is there a thing where if it's impossible, then I just, oh, DNE. Yeah, this doesn't exist. So I'm gonna say DNE. God, I finally got the standard form right. So that was correct the first time. So it's DNE because it doesn't work pretty much. Nice, we got it. Okay, we have one more of those, another identifying thing, and then two big word problems. So let's just go for it. Okay. Number 11. So again, we want to consider equation below. And what is this? We have x squared plus y squared plus, not plus, minus 2x minus 4y minus z plus 5 equals 0. And we want to again reduce standard form. So we can go with that previous strat that we did, which was identifying what kind of equation this is, what kind of quadric surface. Okay, so if we take out the x, let's say we take out the x, what would we get? We get y squared minus 4y minus z plus 5 equals 0. And I mean, we can complete the square, but it doesn't. Did I say minus 5 minus z? Yeah. Now what? Sure. You can definitely complete the square. You can also choose not to. Um, okay, you know what? For this sake, I'm gonna do it. So this is why. What is this? Y plus 2, y minus 2, I believe. Let me check. I'm using a formula here. For completing the square, a of x plus b 2a squared minus square. It was a weak one. I forgot what the formula was. Uh, where was it? Something here. This one. Where was it? Oh, there. Minus b squared over 4a. So minus, oh, plus some constancy. So if we want to apply that, we have y squared minus 4y. We have y minus 4 over 2 squared minus b b squared. So minus 16 over 4. And so we get y minus 2 squared minus 4. How do I know? I can rewrite this. So we have y minus 2 times y minus 2 minus 4. Y squared minus, let me do the FOIL method, minus 4y plus 4 minus 4, y squared minus 4y, which is the same. And after rewriting that thing, we want to plug it back in here. So we get y minus 2 squared minus 4 minus z plus 5 equals 0. And then we can say 1 minus z plus 1 is 0. Now here's the thing. I cannot identify what exactly this is. Yeah, this is icking me out. Oh, I can put the negative one. If I do that. Yeah, now I have like what? Y minus 2 squared. Um, plus 1 equals z. And then, oh, I have a quadratic. Yeah, I should have just realized it was a quadratic. I didn't even need to complete the square. Yeah. How do I know it's a quadratic? Well, z is not squared. I can only pick from three things. It's either a parabola, which in this case it is. It's an ellipse or a hyperbola. Ellipse and hyperbola basically have two different variables that are second degree. This one, only one of the variables is second degree, so this is definitely a parabola. Yeah, it's this one. Y squared minus 4y plus 5 equals z. That's it. So this is so I'm going to note it. It's a parabola at YZ plane, right? Now if we take out the Y, it's a parabola at the XZ plane. Quick and easy. And if we take out the Z, where are you? It's only one Z. Well, to me, this looks like a circle. So just to be sure, I'm going to write it out. There. That's the whole thing without the z. I can complete square. So I can put them here side by side. But maybe put the -5 in the other side. Now I can complete the square. So I have x minus b over 2, so -1 squared. What does this give me? I got x squared minus 2x. I got that plus 1. So it's -1. Then -1. Okay, and then another complete the square here. So we have y squared minus 4y. This is going to be, we did this earlier, -4, was it? Forgot what it was. This is y squared minus 4y plus 4. Also, it's -4. Yeah. So this thing -4 -5. So it is a circle. So this is x minus 1 squared plus y minus 2 squared equals 5 plus, or -5. Oh, would you look at that? If I put this to the other side, I get 0. I actually get 0 here. Um, it's a circle. It's a circle at xy plane. And here I can tell this revolves around the z-axis. So what is this? It's a paraboloid. If we look at our table, or I have a table here actually. I don't know why I didn't do that. Uh, oh, we only have one. Oh, we have two of them. It's an elliptic paraboloid. That's what it is. Yeah. Um, yeah. It looks like an elliptic paraboloid. Because that's the only one that seems obvious. Okay, let's check the conditions. Vertical traces are parabolas, and horizontal traces are ellipses. So what does that mean? YZ plane. So if you were to draw this out, okay, I'm actually gonna do a buffer drawing here of the 3D space. So if I do a 3D space here, and we say YZ is a vertical, so that's a parabola. XZ is a vertical, so again, it's a parabola. And circle is a horizontal. So horizontal is circle or ellipses, and vertical traces are parabolas. So it is indeed an elliptic paraboloid. Now we want to write it in standard form, and we're actually given that here. So z over c, and this one I think, I'm not sure, but I hope it is easier. I hope it's easier. Okay, Let's try to unpack this. Let's put all of these together. Minus z plus 5 equals 0. Maybe we can already put the z on the other side. So I'm going to say plus 5 equals z. And now I can maybe complete the square. Do I complete the square? Yeah, I probably should. Yeah. Yeah, so it was x minus 1 squared. Then I think it was plus 1 maybe. X minus 1, x minus 1, x squared minus 2x plus 1. So it's minus 1. Then we have y minus 2 squared. And I think I subtract a 4 here. Yeah, because minus, I'm just double checking. I should have just left it earlier. Minus 4y plus 4. So indeed it's minus 4. And then I have a plus 5 here. Then this is z. And oh, I get a nice looking formula here. Equals z. Because minus 1 and minus 4 is minus 5. I add that to 5, I get 0. So now I'm left with this thing. Yeah, this looks like a nice formula. I hope it's correct. If it's not, I don't know. We'll try other ways, I guess. Equals z. Looks right to me. And what's the surface? It's an elliptic paraboloid. And if we were to sketch the surface, okay, why does it say sketch the surface? No, I mean write an equation. So let's do that. Write equation at z equals -1 using x and y. So again, I just plug that in the formula right here. So we have x squared plus 2x. Is it 2x? Oh, plus y squared. I keep forgetting formulas. Minus 2x minus 4y minus -1, so plus 1. Because minus z is -1, minus -1 is plus 1, plus 5 is 0. Okay, this is just plus 6. I could stop here and then say this is all good. So I'm just gonna do that. So we have x squared. Wait, but is it possible? Ooh, is this possible? Let's actually simplify and see. So again, we want to complete the squares. Yeah, next time when there's something like this, I'm actually just gonna write out the complete the squares and be done with it. So I get plus 1, so this is -1, right? I think that was what I got earlier. Yeah. And then for the other one, y squared minus 4y, I get this. And I add 6. And then I get -5, and then I get 1. Oh, so I get -1. So this is D and E. There's no such thing as a negative radius. Okay, we do it again. This time we write it when z is +1. So this would just change a bit. This is basically... Oh wait, I'm actually not sure. Let's take a step back and see. So I have x squared plus y squared minus, what was it? Minus 2x minus 4y minus positive 1. So minus 1 plus 5 equals 0. 5 minus 1 is 4. So I make this a 4. Then I do complete the squares again. Minus 1 plus the y part minus 4 plus 4. Oh, would you look at that? That's x minus 1 squared plus y minus 2 squared equals 1. This is possible. It's a unit circle with a different center. 1, 2. That's the center. Okay, I'm just typing this up. Okay, next. Write it again at y is 0. So at y is 0, well, we just use that same formula here. So we have x squared minus 2x. So I'm just going straight to the point here, taking out everything with y. Minus 2x, x squared minus 2x minus z plus 5. So this is a quadratic equation. X squared minus 2x plus 5 is equal to z. Yeah. Done. Wait, is this possible? Yeah, it's possible. Yeah, just use quadratic formula and then you'll be able to get something here. I'm kidding. Yeah, that's for x-intercepts. But yeah, this is possible. I don't think it's not. Okay, then we do it for y equals 2. Not 0, 2. So we have x squared minus 2x. Actually, we have a y squared here. Let's just do that. Plus y squared, so plus 4. So now we have numbers. Minus 2x minus 4y. Minus 4 times 2, so minus 8. Minus 4y minus z plus 5. There. And another quadratic formula, I think. 4 minus negative 8. Here's our constants. 4 and negative 8, 5. 4 and negative 8, that's minus 4. Add that to 5, that's 1. So I have a positive 1 here. Equals 5. Not 5. What am I saying? Equals z. Yeah. Which I think looks possible as well. But again, I'm not sure. I'm not really good not really good at geometry. Okay. Then we do x is 0. Let's say 4. Let's say at. When x is 0, we take out everything of x. So this would leave us with y squared minus 4y. What else? y squared minus 4y minus z plus 5. So you're just multiplying every x by 0. We say, or we see that this is a quadratic formula. There we go. So this is y squared minus 4y plus 5 equals z, right? And then lastly, for x equals 1. Sorry if this is a long video. I'm just trying to fight through this homework. Okay, so when x is 1, let's plug this thing in again. Okay, I'm gonna copy paste just so that's easier for me to just plug it in and be over with it. Okay, nice. We have 1, another x here, minus 2, minus 4y minus z plus 5. So we have uh, y squared minus 4y. This is, I believe, 1 minus 2 plus 5. I'm just going to calculate that. I get positive 4 minus z plus 4 equals 0. So I actually just get plus 4 equals z. And so another quad formula here. Which we're going to see if it works. Okay. Now I'm going to hit submit and see what happens. It would be funny if I got everything wrong. That's funny. But we'll see. We'll see. Hmm. Messed up one of them. Okay. Check the plus and minus signs for all terms in our values. So I messed up at y equals 0. Oh, my bad. So it's supposed to be minus. Yeah, I did plus 2x in the... Okay, never mind. Yeah, it's minus. Let's try again. Hopefully I get it this time. Um, nice. Okay, 2 more. Or no, 3 more. Or 4 more, actually. Yeah, 4 more. Then we're good with this lesson. Okay, right. So here, we want to find an equation for the surface. Consisting of all points. I think I took like 2 hours now. Anyway, we're close, we're close. Of all points um, that are equidistant. Oh, now this one's interesting. So here, we want to find the equation of the surface. We're not just identifying, but we're trying to find an equation given points. From point, so we have 4, 0, 0, and the plane x equals 4. Great. So how do we do that? I don't know. I'm going to look at it. There's a formula. Okay, so you want to recall some formula from a distance from a point to a plane, which I think we did cover. Yeah, it was some formula. And then this is some plane. Okay. So we need to have some point. From arbitrary point. Okay. So we're trying to find the distance from the point to an arbitrary point to our given point, and the distance from that to our plane. Hmm. We have 4x here, 0y. Okay. And just factor out the 4. Mm. So we want the people to be 2. Just square those sides. Also, we expand this thing. Wait, it's my thing right here. Mhm. Okay, yeah. I'm gonna admit that was a tough problem. Yeah. Even in the textbook, we weren't asked to find an equation for a quadric surface, so that one's hard. But yeah, here we can just cancel. Um, uh, I guess I could put the x on the other side. So we have plus 8x. So I could say like, oh, 16 plus y squared plus z squared is negative 2x plus 8x. So that's positive 6x plus 1. Then I could subtract the 16, and then I get 1 minus 16, I get minus 15. I get that thing. So it's a circle equation here. Um, I, I just realized it has to be negative 4. Whoops. This is plus 4. Uh, x minus 1. We have plus 4 here. Plus 4 here. So we have plus 8x. And then a plus 16. And then if I put this to the other side, I get minus 10x. And then I get minus 10x plus 15. So yeah, this is a some circular equation. Okay, I'm gonna stop the video here because it's too long, and I'm gonna um, check this out, see if this is correct. If not, I'll let you guys know in the next video. Okay, I'll see you guys in the next one.